Today we are learning all about capacitance. We've been talking about capacitors or parallel plate capacitors for a while now, and we're going to do a real quick deep dive into their property called capacitance. Before we get into capacitance itself, let's review what a capacitor is. A capacitor is any two equally and oppositely charged conductors, and we can refer to them as electrodes, which is a word we haven't used yet. And they don't necessarily have to be parallel plates. You could have really any two conductors. You could have two conducting blobs that look nothing alike, have one of them be positive, have one of them be equally negative, and that's a capacitor. However, that's an obnoxious capacitor that wouldn't really be useful and would be mathematically annoying. So we're not going to deal with that kind of capacitor, but they do, theoretically exist. It's just any two equally oppositely charged conductors. So far in this course, we've only looked at capacitors that were already charged. But something that's going to kind of motivate our discussion here is dealing with how capacitors become charged. So the steps are written here, and I'm going to draw as we go through them. So step number one is that you have to connect a capacitor to a battery or some other source of potential difference, but we're just going to call it a battery. And I'm going to show that over here. This is going to be the capacitor right here. Right now there's no charge on it because it's an uncharged capacitor. And we're going to hook up each electrode to the sides of a battery. I'm going to draw a really crappy battery right here. This is my battery. I'm not using the schematic symbol, but that is the battery. And charge is going to flow from one terminal to the plate. Now we're going to get into circuitry and the way charge flows and conventional charge and whatnot in circuits. So if you know about this stuff, ignore the fact that I'm using conventions a little bit weird. We're just trying to get the idea here. So what's going to happen is that electrons or electricity is going to flow from the battery onto the plates. So from one terminal, electrons are going to start flowing around onto this plate, and because it's a conducting plate, it's going to fill up with some extra electrons because the charge spreads out evenly over a conductor. But what's important here, or part of what's important here, is the battery. So the battery is a source of potential difference. So it'll have some potential on one side, we'll call it VA, and another potential on the other side, VB. And this generates a potential difference between the two. So the potential on side B has to match everywhere around the circuit because it's all conducting. So on a conductor, the charge is going to spread out evenly until the potential is all the same. That's just a property of the conductors. So the electrons flow around until they fill up this plate so that this plate has the same potential as that terminal. So this whole right side has the potential VB. And then all of these electrons over here on the right plate are going to make an electric field because charges generate electric fields. That's one of their properties. And the electric field points towards the negatives, just like we already know. So all of the electrons on this other plate over here are going to be repelled by the other plate, which is negative, and they'll go against those field lines because electrons go backwards from the field vectors. So the electrons are going to abandon this plate and they're going to flow around to the other side. And as they abandon that plate, this plate is going to become more net positive until the things are equal. And the way that that is going to end up is that this side will have the same potential as this side due to the same conducting properties. So the capacitor becomes charged that way, and it ends up with the same potential difference as the battery, which is something that is super important for us to know moving forward. The capacitor becomes charged with the same potential difference as the battery. Now, if we decided to cut the battery off, take the battery away, we didn't want the battery anymore. I'm going to erase here to cut the circuit off. There is no way for more electrons to get to one plate to come back to the positive and make it neutral. And there's no way for the extra electrons to escape the negative plate. So they stay charged exactly like they are. And this is one way that charge can be stored. And it gets stored in circuits in capacitors frequently. That's the main use of capacitors in electronics, is to store a little bit of charge. They're actually used a lot of times to help out. Well, they're used in like storing charge for batteries for various electronic devices. They're also used in circuits to provide a little bit of potential difference to the circuit in case the battery stops working for a second or it cuts out. If there's an issue with something else, capacitors can provide that little boost it needs to keep the circuit going instead of having it fail. So now that we know what capacitors are, how they become charged, we're going to talk about their property, capacitance. The definition for capacitance is that it is the constant of proportionality for the proportion between charge and potential difference of a capacitor. And the equation is kind of an easier way to represent that is right here. It says that charge equals the capacitance times the potential difference over the capacitor. So if we wanted to write that more as a proportion with a constant, we could write it as C, the capacitance, is the constant proportion between Q and change in potential over a capacitor. So what this basically says is that charge over potential difference is going to be constant in a capacitor, and the constant that they're equal to is the capacitance. The capacitance of a capacitor is determined by its shape, its size, and the spacing between the electrodes, or the two plates, but it is not dependent on charge or potential difference. And the unit of capacitance is the farad, named after Faraday, and a farad is defined as 1 coulomb per volt. All right, and here we're going to do a quick derivation for figuring out how to calculate capacitance from the characteristics of a capacitor. And you can see the equation there. That's the equation we're going to end at, but I'm going to show you how we get to it. I don't know about you, but I never like it when people just throw a random equation at me and then say, use it. And I have no idea where it comes from. I don't like that. So I do like to show derivations for these things. And we're going to start with the definition for capacitance, which is that it is the constant of proportionality between charge and potential difference. C equals Q over delta V. And we're just going to make some substitutions with things we already know. So we know that delta V, when we learned this last class, that delta V equals the electric field times the distance between equipotential lines. Please, hopefully you learned that. And the distance between equipotential lines for a capacitor is the distance between the capacitor if you're looking at the voltage over the whole capacitor. So it's just the difference between the plates here. And we're just going to substitute that in. The capacitance equals charge on the capacitor divided by electric field in the capacitor times the distance between the plates. And we also know from way back when that the electric field inside a capacitor is equal to charge on the capacitor over permittivity of free space, or vacuum permittivity, times area between plates. That is field inside a capacitor. So we can just slap that sucker right on in. You get capacitance equals Q over D times 1 over Q over epsilon naught A. So we're just going to do the reciprocal, epsilon naught times A over Q. And these Q's very beautifully cancel so that capacitance is not at all dependent on charge. And you get that capacitance is equal to epsilon naught, which is permittivity free space, times the area divided by the distance between your two plates, which is pretty easy peasy. So you can calculate the capacitance between two parallel plates with just their area and the distance separating the two. And note that if you increase the distance between the things, you decrease the capacitance. And if you increase the area, you increase the capacitance. Now, another thing to note here is that this is using the permittivity of free space. So we are assuming that between the two capacitors, there is nothing. There is not air, there is not a material, it is a vacuum. And we will look later at how to deal with it when you have something else in the middle, and that's called a dielectric. We'll be looking at those in a little bit. But before we move on to dielectrics, let's do a quick little example using just a regular parallel plate capacitor. So this question says that the capacitance of a practical parallel plate capacitor is quite small in the picofarad range. Suppose you want to make a 1 microfarad capacitor using square plates separated by 1 millimeter. How large do the plates need to be? And we're going to find that in terms of side length. And we're going to use that equation we just derived, which is that the capacitance is equal to epsilon naught times A over D. So we're just going to plug some of these things right in. We're solving for A, so we're going to leave that alone. We know capacitance that we're looking for is 1 microfarad, so that's 1 times 10 to negative 6th farads, which equals epsilon naught, which is 8.85 times 10 to the negative 12th with some unit that I'm not going to go look up right now. I know I should, but it's late. I'm not going to. We're going to multiply that by the area, which is what we're looking for. We don't have. Divide by the distance between the plates, which is 1 millimeter, 1 times 10 to negative 3rd meters. So you do some math to figure that out in a calculator. And you should get, or hopefully you should get, something like 112.99, and that's an area, so that is meters squared. Now to find the side length, since this is a square plate capacitor, you just take the square root of that, which will get you 10.63 meters. That's a pretty dang big capacitor. All right, so next up we have dielectrics and how they affect capacitance. And to understand how this works, you have to go all the way back to thinking about polarization. So polarization, we learned about in the beginning. Polarization is where you take something that is neutrally charged, so like a regular atom is neutrally charged. If you look at this one, it's got the same number of protons and electrons, so it's neutral. And you drag some charge close to it. So that's going to be like happens over here. So if you put a negative charge next to an atom, it's going to attract the nucleus and repel the electrons. So the nucleus is going to be pulled towards it, and the electrons are going to be pushed away, like that. Or the same thing would happen if you put a positive external charge. It would attract the electrons and push the nucleus away. And if you put an atom between a positive and negative, the effect is going to be doubled. So what that means is that overall, inside the atom, you end up with a positive side and a negative side. So in this one here, the nucleus is the positive, well, and always the nucleus is the positive, and the electron cloud is the negative. So those two things are separated out. And they are of equal charge, which makes them basically like a baby capacitor. And inside the baby capacitor, you have an electric field. So the electric field inside goes from positive to negative. So inside a polarized atom like that, you have tiny little baby electric field, which is pretty cool. So if we look at an atom inside an electric field, this same kind of thing happens. So in an electric field, positive charges go in the direction of the arrows, or are pushed in the direction of the arrows. So positive charges go that way. So if we've got an atom, the positive nucleus, which I'm going to represent as several charges, gets pushed towards the right, and the negative charges, which go backwards from the electric field, are going to get pulled to the other side. So there's going to be an induced charge on the atom. And inside that atom, due to these induced charges, there's going to be a little baby electric field. And that baby electric field points opposite the big electric field. So it cancels out inside a tiny little bit of that electric field, which is a really weird concept, but it does happen. But you can take that and you can apply it to all of the atoms inside a capacitor. So we're going to look at that here. And I'm going to draw the big electric field lines for the whole capacitor in yellow, and then I'll do the little atoms next. So in a regular capacitor, from positive to negative is the direction the electric field goes. So like this. Got electric field running across the capacitor. And inside every little atom, these giant circles are supposed to represent atoms, you're going to end up with induced positive and negative charges. The positives are going to go to the right side. I'm just going to draw one positive to indicate the net positive. I don't want to draw like a million positive charges here. And then the negatives are going to be pulled backwards on the electric field vectors towards the positive side. So that every atom here has an induced charge due to the electric field. And that induced charge creates a tiny field going backwards like this, which is pretty cool. Let me draw all my baby electric fields. I titled this slide Pictionary version because I knew I was going to have to do a lot of drawing. All right, so there's all the little baby electric fields. So what happens is that inside the whole capacitor, the electric field is going to decrease because you're adding all the electric field vectors up. So the electric field is now slightly opposed by all of those little polarized atoms, and the electric field decreases. Now we know that the voltage across a capacitor is equal to the electric field times the distance. So if we decrease the electric field, that potential also decreases. The potential difference decreases. So we decrease the electric field, the potential decreases, potential difference. And if we rewrite this in a better way, so it's actually the constant of proportionality, capacitance equals charge of Q over delta V, you see that if V decreases and Q stays the same, capacitance has to increase, and Q does stay the same because we're not changing the charge. So the field decreases and the potential difference decreases, which makes the capacitance increase if you insert a dielectric. Yeah, so I switched the order of these slides before I started making this because I thought it would be better to draw all of the pictures right after we'd drawn the other picture, which is probably true. But in doing so, I forgot to mention what a dielectric actually is. So a dielectric is the thing we put in the middle of the capacitor and the other thing. It's got a bunch of atoms that are doing things. It's not a vacuum anymore. And it's specifically an insulating material that's placed inside the capacitor, and it changes the capacitance. So it's important that it's insulating because if you stuck a conductor in between two charged plates, then all of the charge would just equalize out and you wouldn't have a capacitor anymore, or at least you wouldn't have a charged one anymore. So they have to be insulating. Every atom in the insulator polarizes, but it doesn't lose an electron because these are insulators where electrons don't flow. So the electrons still stay with their respective atoms. So that makes a bunch of little electric fields that point opposite the field of the capacitor and decreases the overall field. So we just saw how all that worked. And it means that when you insert a dielectric, the capacitance goes up. So you might be wondering why this is important, why it matters, and why you would even want to increase the capacitance in the first place. So a few minutes ago, we said that capacitors are used to store charge. So if you increase your capacitance, which is given by the equation C equals Q over delta V, if you increase that capacitance, that means you can also increase the amount of charge that is stored for the same potential difference. And your potential difference is driven by a battery. So if you want to keep the same size battery but get more charge stored, you have to increase the capacitance. And inserting a dielectric is a really good way to do that. And to figure out just how much that the dielectric affects that capacitance, you have to know the dielectric constant, which is this variable kappa. So different materials have different types of atoms, and the different types of atoms become more or less polarized in an electric field just due to their properties and their charge distribution and their electron orbitals and all sorts of crazy stuff. So each material is assigned a value that's called the dielectric constant. And it's basically just a constant that tells you how much the capacitance changes without you having to do any extra calculations. So the equation for figuring out the capacitance with a dielectric, so C without the subscript is with the dielectric, is you take that constant, the dielectric constant K, for that specific material, multiply it by the capacitance if there was no dielectric. And that'll tell you your new capacitance. Pretty cool. And this dielectric constant is actually calculated from a different constant that is a property of the material called its permittivity. So we talked briefly on another day about this constant, epsilon naught. This is called vacuum permittivity or permittivity of free space. Either of those means the same thing. So there is a certain way, certain constant for when charge moves through empty space, and then another one for when it moves through a material. And the permittivity of a material defines the way the charge moves through it based on that polarization. So to find that dielectric constant, you just take the ratio of the material's permittivity to the vacuum permittivity. And this actually isn't something that will be on the AP test because it's not included in the AP curriculum, but I think it's an important thing to consider. So before you go, let's look at an example of a parallel plate capacitor that is using a dielectric. We've got a parallel plate capacitor charged using a 100 volt battery. The battery is removed, and we're going to slide a dielectric between the plates. So I'm actually going to draw this because I need to think about it. So we're going to stick this into a circuit. This is the schematic symbol for battery. And the battery is going to charge the thing up. So if we call the potential difference between the terminals 100 volts, we can make this side of the capacitor 100 volts, this one 0. So we know the potential difference between the two. And then circuit's removed. Now it was never closed because I didn't draw the line completely, but that's whatever. And to know which side has positive, you know that the positive side is going to have more potential than the negative side. So this one's positive, this one is negative. So there's our capacitor. We've charged it up to a potential difference of 100 volts. Battery is removed, and we're going to put a dielectric in here. Okay, so now this is going to be filled with something else. Filling the space inside, the capacitor voltage drops to 30 volts. What is the dielectric constant? So we have the equation from way back when that was the definition of capacitance. So you get, wrong color. You get capacitance is the constant of proportionality between charge and potential difference. And if you multiply that out, you get capacitance times potential difference equals Q. Now, the charge on the capacitor, since we've disconnected the batteries, stays the same the whole time. So you could say capacitance initial, which is before the dielectric, times the potential difference on the capacitor initial before the dielectric equals the charge, which doesn't change, which also equals the capacitance after you insert the dielectric times the voltage after you insert the dielectric. So you can leave Q, the middleman, out, and you can say capacitance initial times voltage initial equals capacitance final times voltage final. And some of these things we know, so we'll plug them in. We don't know the initial capacitance, we'll leave it. We do know the initial voltage is 100. I'm going to make that a coefficient because it looks prettier. 100 times initial capacitance equals final voltage. Voltage drops to 30, so that's 30 volts, times the final capacitance. Sorry, my handwriting looks gross. And what we're looking for is the dielectric constant. So we do know that the dielectric constant equation says that the capacitance with the dielectric equals kappa, the dielectric constant, times the capacitance without the dielectric. So you can rearrange that around to get the dielectric constant is the proportion, the ratio of capacitance with the dielectric to without the dielectric. So if we're going to use this that we ended up with, plug it in there for proportions to get the dielectric constant, we have to know which one is with the dielectric, which one is without. So the final one is with dielectric, I'll abbreviate that as DE. This one, initial, is without dielectric. So we can just divide these two things to figure out what the constant is. Now, if we rearrange this equation down here, we can get to something like that. Let's see how to get there. We have to put the capacitance with the dielectric on top. So that's CF. We have to divide that by CI, the capacitance without it. So we'll divide both sides by CI. So you get 100 equals 30. CF over CI is the dielectric constant. Divide by 30 on each side. And get that the dielectric constant is 100 over 30. So 10/3. And the dielectric constant has no units because you're dividing a capacitance by a capacitance. So no units there. All right, guys, thanks for watching. Please let me know if you have any questions. Get to work on that one section of your homework that covers this for 21.7. And I'll be talking to you again tomorrow.